I want to start off first with the sampler, how to set up a sampler in Omni 3000 or 6000. There's no configuration settings for it, so you basically just have to do it with the digital outputs and or the Boolean and variable statements. If you're just going to set up one sampler, let's say for a meter run or a station, it's pretty simple. So we'll just go to the digital IOs. And in this case, I have digital number 12 configured. And in this case, 1801 is what I assign to that digital output. And if you want to know what 1801 is, then you go up here to the very top and you can see the magnifying glass on the ribbon bar, and that's the database browser. So we'll click on that and we'll clear every filter we have in there by hitting that clear filters button. And then we'll just highlight any register in there and just type 1801 and it takes me right to it. So as you can see, it tells me the station positive gross pulses. So that's what 1801 is. So basically for every barrel that the station counts, that's a pulse that is generated by the flow computer in register 1801. If it increments by, let's say, 5 barrels, then that's 5 pulses in 1801. But the way I have this set up is pulses per barrel here, pulses per unit. In this case, unit being barrel. I'm telling it to output a whole pulse for every 10 barrels. So what I do is, if I want to know what number to put in there for every 10 barrels, I say I always take the number 1 and I divide it by 10 and I get a 0.1, and that's what I put in there. If I wanted to output a pulse every 20 barrels, again, I take the number 1 and I divide it by 20 and I get a 0.05. So that's what I would put in there. So it's basically 0.05 pulses per barrel. And when I get 20 of those 0.05, then I'm going to get a whole pulse that the Omni will output. In this case, of course, it's every 10. So 0.1 is how many barrels a single pulse represents. So until I get 10 of those to give me a full pulse, then it will output a pulse by a digital output number 12. So if anybody has any questions on that, please let me know. And so that's basically it for setting up the sampler. Now, if I wanted to do just a sampling for meter 1 and not the station, I come into my browser again, and I just happen to know at the top of my head what it is, but it's 1101 for meter 1. So I could just type in gross pulses here. And it says meter 1 is 1101. Then you got 1201 for meter 2. Meter 3 is 1301, 1401. Then for the station, which is what we're using here, that's 1801. So it's really just that simple. Now for the pulse width, if we up there is the help icon, but it's got an arrow with that question mark. So we click on it and we bring it down to that pulse width setting. And we can see that it brings up our help. And we're going to click on, let's see, this is a accumulator or pulse output. So that's what we look for here, accumulator or pulse output. And the pulse width is what we were looking at. As you can see, pulse width. So it says enter the width of the on and off time of the pulse to be output. Pulse width is measured in 10 millisecond ticks, right? So if I put a 1 in there, that's 10 milliseconds. So it says a pulse width of 5 ticks would provide a 60 millisecond on time and a minimum 60 millisecond off time. So actually, let me go back and correct what I just said, because if you put it to 0, a pulse width of 0 is 10 milliseconds. So there's an offset of 10 milliseconds there. So it's telling you 5 doesn't really mean 50 milliseconds. It means 60 milliseconds on and 60 milliseconds off. So in my case here, I put 100 in there. So 100 times 10 is going to be 1,000 milliseconds. And then you add the other 10 milliseconds. So it's 1,010 milliseconds. So it's just slightly over 1 second wide. And that's the on and off as well. So you have to be careful that you don't make that too big, or else you start accumulating pulses in the buffer of this output channel. So that's about it for sampling. As far as setting up a sampler in the Omni, it's pretty simple. But now, if we want to do something else, let me bring up my folder here that shows me some other examples of setting up samplers. Let me see, not the right folder. Okay, this one is sharing a sampler between two Omnis. So it says here in this example, the defined station spans more than one Omni. So basically, you can have, let's say, a couple of meter runs in one Omni and a couple of meter runs in another Omni. And, or maybe you have 4 and 4, right? You're allowed to configure 4 meter runs in one Omni and 4 in the other. Or maybe you just have 5, so you'd have 4 and 1. 4 meter runs configured in one Omni, 1 meter run configured in the other Omni. So we're going to simulate sending gross flow volume increment pulses from Omni B to Omni A. So the way we do it here is this is a scratch pad. 7501 is a scratch pad. And this is variable statement 7025. So let me switch back to Omnicom. Close the help here. Go to Boolean and variable statements. As you can see, variables 7025 is where the variable statements start. 1025 is where the Boolean statements start. So these are all, consider them like empty statements. By default, they're all empty, so you have to write something into them if you want it to do anything. So in this example, let me bring it back up. We're saying in statement 7025, we're going to write this statement. 7501 equals 7501 plus 5870. So we have to know what 7501 is first. So let's look it up in the database browser. Clear the filters. We type 7501 and it takes us there. And it says it's just a scratch pad variable, right? So it's just a scratch pad, an empty register. And you get 99 of those for triple float, IEEE float registers. So 7501 to 7599 are all scratch pad variables of the IEEE float type. You also have integers like 5501 to 5599. They're also scratch pad 32-bit integers. You also have 16-bit registers that are scratch pads, 3501 to 3599. So now we know what that 7501 is. And then 5870. So we have to know what that is. So let's go back there again. And we see that the station increment integer grows, right? So the station increment integer means, for gross totals, means every 500 milliseconds, it's going to give you pulses, or actually going to increment that totalize you to tell you how much of an increment that totalizer moved in that 500 millisecond update cycle. And again, that's for the station. So if we wanted to know what it is for the meter, for meter one, let's just do a search on increment integer. And let's just do it for meter one. And there it is. 5170 for the gross. If you wanted to look at the net, the mass, and the energy, or in this case, because it's liquid, it's gross, net, mass, and NSV. So those are the other registers. So in this case, we're looking at 5870, which is the station. So 7501, again, is the scratch pad, and 5870 is a 500 millisecond gross increment. So by saying 7501 equals 7501, we're keeping what was in there in the previous cycle in 7501 and adding 5870 to it. If it just said 7501 equals 5870, then we would be throwing away what was previously in 7501. So by saying 7501 equals 7501, we're not throwing away what was in 7501. We're keeping it and then adding the increment from 5870 in that 500 millisecond cycle. So that's an Omni B, right? So in Omni A, we do a peer-to-peer transaction, and we go read that scratch pad 7501 only for 1 point, and we stick it in 7501 in the A Omni, right? So this is the B Omni, the source index is the B Omni for only 1 point, and the destination point is the A Omni, and we stick it in the same scratch pad register 7501. We don't have to, but in this case, just for simplicity, we're going to put it in the exact same register in the A Omni as in the B Omni. So the peer-to-peer transactions, we'll go look at that. So in this case, we would say maybe the slave ID over there is 2, and we would go read 7501, 1 point, 7501. Right, so we read from slave ID 2, which is the other Omni. We read from register 7501 for 1 point, and the destination in the A Omni, in this Omni, in other words, is 7501. So that's how we would set that up. Okay. So then this is in the A Omni. So 7501 minus 7502. Again, remember that 7501 to 7599 are scratch pad registers. But what's in 7502? Well, we had to go further down and see that at some point we transferred what was in 7501 to 7502. And now the flow computer continues to process the remainder of the variable statements, and then it cycles back around the next 500 millisecond cycle. So we're saying whatever's in 7501 right now, subtract 7502 from it. So 7502 is basically the previous cycle, right? So we saved 7501 in this statement 7027. We saved 7501 and 7502 so that we could subtract it later on from the new 7501. And then here we say 79 equals 5870 or 7025. And I know this gets a little complicated, but let's look at what 7089 is. So programmable pulse output register. Now, you just have to know that 7089 through 7099. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 registers. Those 7089 to 7099 are internally tied inside the Omni to registers 1089 to 1099. So 7089 through 7099 are internally tied inside the Omni to 1089 through 1099. So 7089 or 1089, although we have to write it as 7089 here, we say 7089 equals 5870. And we already looked at 5870 earlier, and that was the station 500 millisecond gross increment for this Omni, right? 7501 was for the other Omni. 5870 is for this Omni. And it says plus whatever's in 7025. And this was the increment, remember? The 500 millisecond increment in 7025. So we're taking the current increment in the A Omni plus the increment from the B Omni, and we're putting that into 7089, which the Omni internally creates pulses in 1089 so that you can output those to a digital output. And in the remarks here, we say assign 1089 to digital IO, right? Digital output is what really it should say. So we're going to have to find out where we're assigning 1089. So let's go look at the digitals. Actually, I don't think I have this flow computer for that, configured for that. But what let's see here. Yeah, here it is. I say 1089 because I'm simulating pulses on this one, but if it was for a sampler, instead of assigning 1801 here, I would assign 1089, and it would fulfill the same purpose. It would stroke that sampler for the gross totals in Omni A and Omni B. So it says assign 1099 to the digital Omni that will be driving the sampler. So in this case, with this Omni, it would be digital 12. So I know this is a little complicated, but if you need a better explanation, you can just call in to CRT Services and get with me, and I'll try and explain that a little better. Okay. Let me see what else I can find. And this is sharing a sampler between 3 Omnis. So it gets a little bit more complicated. So you got a C and a B and an A Omni. So in this case, I'm setting up two different transactions to go read from those Omnis. And then I'm basically doing pretty much the same thing as I did over there, except it takes more statements to do this. And then I assign 1089 to it. So if you need help with this, you can always call in to CRT Services and ask for Isaac, and I can provide you with these files here, these examples. Another thing I want to cover is, and this is very important, that kind of does it for samplers, but another thing that I want to cover is writing a Boolean statement for this setting in here, the active frequency setting under the meter run setup. In this case, the Omni defaults to 0 hertz. And what this is saying is that at 0 hertz, the meter will always be considered active whether you have flow pulses or not. Whether you have flow or not, the meter is always considered active. So what happens is if you stop your flow and then you end your batch, the Omni will close that batch, and because it sees that the meter is active with 0 hertz in there, it will immediately start a new batch. Won't totalize anything for a while until you really start flow. You actually start flow. But it will start the batch right away with a new time and date. If you put 5 hertz in there, 10 hertz, whatever number you want, the flow meter is not considered active until it reaches 5 pulses per second or higher. Not 5 pulses, but 5 pulses per second or higher, because that's what frequency is measured in, is in hertz, and that hertz is always in seconds, pulses per second. So what happens though, let's say you have 4 pulses that come in as noise pulses when you have this set to 5 hertz. So you get 4 pulses. They may be in one cycle or they may be spread out through different cycles. The Omni does not throw them away. It keeps them in a buffer. And then let's say maybe 10 seconds later, it gets 3 noise pulses. So now you've got 7 noise pulses. And then maybe a minute later, it'll collect 4 noise pulses. So now you got 11 noise pulses. Again, it puts them in a buffer. It does not throw them away. So what happens then when it finally reaches a point where you start flow and you get 5 hertz, 5 pulses per second or above, then the Omni will consider that a new batch and gives it a date and time stamp, the current date and time stamp. And then those 11 pulses that it had, it adds them immediately, right? Now, sometimes you don't want to do that. You want to throw those noise pulses away. So what you can do, and actually, I think there's some help in here. So let's go ask for help for this setting. And we already talked about, you click on that arrow and question mark icon at the top on the ribbon bar. You bring it down to active frequency. And see if I can this down. It will be under the alarms area. So active frequency, yes, it gives you an example in here. So if you wanted to throw away those noise pulses and not add them when the meter becomes active, you write a statement similar to this. It does not have to be in Boolean statement 1030, it can be elsewhere. So let's go here. Now 1030 in my case is already in use, so I would actually write it up here. 1736 is equal to not 1105. That slash means not. So turn off meter 1 flow if not greater than the active frequency. And it gives you the other flag here, or the other command points where you can turn the other meters off as well. 1737 for meter 2, 1738 for meter 3, 1739 for meter 4. So let's just write that statement here in 1027. So we'll say meter 1, enable, disable. And apply that. Now in my case, I meter 1 flow pulse is assigned to input number 7. So I'm going to go to the diagnostic mode by clicking on that wrench up there. And by the way, if you don't know what these mean, you can go to Actions and go to Diagnostics through here. So you go to Diagnostics, we'll see the islet overview, and we could see that I have 50 hertz coming in on that input channel, which is meter 1 flow pulses. So go back to the configuration. Now, if I put 51 hertz in here, or let me just do that, 55. So now I'm going to go see if I have flow or not. And this is wind panel, so it mimics the keypad. So I'm going to say gross meter 1 display. And it says 0 barrels an hour, right? So it's turned off the totalizers for that meter is what it did. Now I'm going to say 5 again. And now I've got flow. All right, so it did not turn the meter off. It turned it back on because now the meter is considered active. So that's a statement that you can write for each one of your meter runs. So 1736 would be equals 911.5. Now for meter 2, I would say 1737 is equal to
Isaac, I think we lost your audio again.
you did?
There we go. It's back.
Okay. All right. Let me start back on this again. So 1736 and 1737, they're the disable meter 1 and meter 2. Also enable meter 1 and meter 2. It's the same command register. And it's just a Boolean bit. Now, if we say, or if we look for 1105, okay, well, I have to do it up here, I guess. Okay, 1105 says it's the meter 1 active flag. So it's actually the meter 1 active / inactive flag, right? So when that frequency goes above that 5 hertz that we put in the active frequency setting, 1105 will come on, right? So in this case, let's analyze this statement. It says 1736, which is the command point to turn on or off meter 1, equals, I'm saying not 1105. So whatever the value of 1105 is, I'm nodding it. I'm inverting it. Right. So let's say the meter is not active. Right. So if the meter is not active, 1105 is going to be a 0. So I send the opposite of that 0 to 1736. So the opposite of 0 is a 1. So 1736, when I set it to a 1, it's going to disable meter 1, right? But now when the meter becomes active, if I get 5 hertz or above, then 1105 is going to be a 1. And the opposite of a 1 is a 0, so I'm going to send a 0 to 1736 to enable the totalizers. And the same concept applies for meter 2. Okay, so That's about it for that setting. It's important that you know how that works, that you could be collecting a lot of noise pulses and the Omni will add them up if you don't have that statement. It'll add them up when the meter becomes active. And I talked about this when this was the very first one. It was just the setting on the digital point, and that was it. And again, I can make these files available to you if you need them. Just call into CRT Services and ask for me, or send an email, either one. You can send the email to service at CRT. CRT.services. Again, service at CRT.services. And here's a force day in command. Sometimes you want the flow computer to end the day when you end the batch. And sometimes they do this because they have an in-house database where it's a custody transfer metering point, and they want in that database to have the daily totals that they want their customer to log into their database, into customer A's database. Customer B logs into customer A's database to see how much flow went to them on a particular day. But the batch may span 3 days. So at the end of the first day, there's not going to be a batch end. There will be an automated day end. And it's going to collect how much flow went to that customer for that day. On the second day, the batch is still going, and at the end of the automated day end, it will tell that customer how much flow they had going to them. On the third day, finally you end the batch, and you force the day to end as well, so that customer B, when he logs into customer A's database, he can see how much flow went to him on that third day as well. So if you add the 3 days together, then those 3 days should equal the same totals as the entire batch for that customer. So that's what the force day end is about. API instituted this requirement many, many years ago. So basically, 2741 is the command to force a day to end. You've got 27, 42, 43, 44, and 45. And then you've got flags where the flow computer tells you that it acknowledges that you ended the batch. So 1N59 is actually 4 different registers. It's 1159 for meter 1, 1259 for meter 2, 1359.
Isaac, I think we lost your voice again.
Why? Not sure.
There we go. It's back.
Not sure what's happening. But there are registers that maintain this is the day start time of the current day, the day start date of the current date for that meter. Again, this is 4 registers, 4126, 4226, 4326, and 4426 for the 4 meter runs. And then when it closes the day, it moves that data over into the previous day registers to record that day's start time and date and the end date time and the day's end date as well for each meter run. captures your previous day closing totalizer values and your system cumulatives as well in 5894 and 5895. In this example, we're saying put the following into Boolean statements to cause a forced day in at the end of each batch. So 2745, we can see that 2745 is the forced day in for the station. So we're saying 2745 equals 2745, and the plus symbol means or in a Boolean statement. It does not mean add or plus. It means or in a Boolean statement. So you have to be careful the way you use these operators in the Boolean and variable statements. They don't have the same functionality. And here, the reason you say 2745 equals 2745 is because it is a command point, and you never want to change a command point. Or let me take that back. You usually do not want to change a command point not to equal itself, because usually 2745 can be written to via Modbus, or the day can be ended from the front panel of the flow computer, right? So if you just say 2745 equals 1835, right? And we'll see what 1835 is. Well, it's not in here, so let's go look it up. Let's clear our filters. It's a station batch in flag. So that's basically an acknowledgement that the station batch ended. So he's saying that's 1835. And then that's the command, of course, to force the date to end on the station. So we're saying go ahead and end the station from either the keypad, which would be this, or Modbus, and send it to itself at 2745. Or if the station batch is ended, go ahead and force the day to end for the station as well. And 1112 and 1212 are the meter 1 and meter 2 batch end acknowledge flags. So we got different command points for forcing the day to end on meter 1. Remember, this was the station here. This is meter 1, and this is meter 2 command points. And these are the batch and acknowledge flags for each one of those meter runs. So we're doing the same thing here for meter 1 and 2 as we did for the station. But if the station is defined as if the meter run is defined as part of the station, then you don't have to do that one and this one and this one. So let's see what I have my station defined as here. So I'm saying 1 + 2 + 3 + 4. So all of them are in there, all the meter runs. So if I go back here, then that one is going to do a batch end on all 4 meter runs. Or I'm sorry, well, the station batch end will do a forced day end on all 4 meter runs, because all 4 meter runs are part of the station. So basically, if you in the batch on the station, you send the command to end the batch on the station, it's going to end 5 batches. It's going to end meter 1, meter 2, meter 3, meter 4, and the station batch. And then if you write this command to force the day to end, then it's actually going to end the day 5 times on meter 1, meter 2, meter 3, meter 4, and the station. And then it will immediately start a new day. And I want to add that in later versions of firmware, Omni actually added an option in here to force the day to end. Let me see if this one has it in there. Here we go. Automatic day end on batch end. So this was not always here. So Omni added later so that you wouldn't have to write the statements. Now what happens is if you have your batch set to automatically end at the end of your contract day, then the Omni will go ahead and end that batch, and it will do an automatic day that always does that at your contract hour, and it will not again do a forced day in. It already knows that you had the day end automatically at that same time that you ended the batch, so it will not do a double day end. And that was sometimes a problem if you wrote the statements. Okay, let's close this one. Well, okay, here's another one. Detecting a proof sequence end. And that's whether it succeeded or it aborted. I tell you what, we can go ahead and take about a 10-minute break in case you need to go to the restroom or get a drink or something, and we will be back at 10:13. And we'll start at 10:13 sharp. And then we'll come back to this.
All right. Thanks, Isaac. See everybody back in 10.
Okay, let's go ahead and get started again. So detecting a proof sequence end, successful or aborted. We have some statements here. First of all, we have to look at 1911 and 1912 and see what they mean. Everything else is referenced in here is pointing to a Boolean statement. We know that 1025 all the way to 1099 are Boolean statements, as we discussed earlier. And here it's pointing to 1028 in statement 1027. And then in statement 1029, it points to 1025 or 1027. So the only ones that we really have a question about are 1911 and 1912. And I put those descriptions in this document. 1911, when it goes high, means proof sequence completed. 1912, when it goes high, says proof sequence aborted. So it didn't complete for one reason or another. So it says 1911 and 1912 are zeroed or reset at the start of a proof sequence. One of them then goes high, depending on whether the proof sequence was successful or aborted. And the above Boolean statements capture the change from 0 to 1 for either of the two registers to indicate the proof sequence has ended. So you'll never see 1911 and 1912 both true. You'll see them both 0 at the beginning of a proof sequence when they're reset, but you will never see them both at a value of 1. Only one of them goes high at the end of a proof sequence, whether it's successful or aborted. So 1911, in that symbol, the asterisk means X or, not or. Remember that the plus symbol in a Boolean statement means or, but in this case, the asterisk means XOR. And all XOR means is the opposite of. So 1911, the opposite of 1026. And what is 1026? It's 1911 in the previous 500 millisecond cycle. right? So the Omni starts to process 1025, then 1026, then 1027, and it keeps those states in its buffer so that you can compare in the next cycle. So that's what statement 1025 is doing. It's saying I'm looking at 1911 and checking to see if it's the opposite of 1026. Well, so what does that really mean? It means that in the previous cycle, let's say it was a value of 0, and now in this cycle, it's a value of 1. So basically, it has changed. Or it can even go the other way around. It might have been a value of 1 in the previous cycle, and now it's a value of 0. So again, it has changed. However, the qualifier here, the ampersand sign, means and 1911 has to be true, right? So here in the first part is just checking to make sure that it has changed from the previous cycle to this cycle. But then here it qualifies it with and 1911. Since it does not have the not symbol, in other words, the forward slash in front of 1911, it says it's checking for 1911 to be true. So basically what this is doing is making sure that it went from a 0 to a 1. So if this was a 0 in the previous cycle, which transfers to here and here. So if it was a 0 the previous cycle and it's a 1 now, that means they are opposite. It's toggled. And it's checking to see if it's a 1. So basically it's checking for a state change from a 0 to a 1. So when that 1911 goes from a 0 to a 1, this statement will be true. So then now it captures the current state of 1911 and puts it in 1026 again, so that if we need to compare it the next cycle, we can. So 1912, again, it does the same thing here for 1912 as it did for 1911 up in statements 1025 and 1026. So in statements 1027 and 1028, it does the same check for 1912. So here it checks to see if it is toggled from a 0 to a 1 or 1 to a 0, but then here it qualifies that and says, I want to check to see if it changed from a 0 to a 1. So you know that at the end of a proof sequence, one of these is going to be true, right? Either 1025 or 1027 will be true. And that's what we're doing here in statement 1029. We're checking to see that one or the other is true. The 1911 or 1912 has changed from a 0 to a 1. And then we say you can then choose to assign 1029 to a digital output. So basically, let's say you have a PLC that wants to know when a proof sequence is ended. You can assign 1029 to a digital output, and the PLC will know that a proof sequence has ended when it goes from a 0 to a 1 on that digital output, because one of these toggled from a 0 to a 1. So that's basically it for here. Now, let's look at that 1029 that we would assign to a digital output, because I want to show you how the digital outputs can change a little bit depending on what you assign to them. So in this case, I'm just going to assign 1029 to it, and that's going to be a control output, right? Now let's say I try to assign it as an accumulator. Let's see what happens. Invalid assignment for type selected. It knows that 1029 is a Boolean statement, and it won't let me do it. So if I say this and apply that, again, it tells me it's invalid. I can't assign it as that type. But if I do this, control output, it takes it. It knows that's valid. So it does the check for me. Now the delay on and delay off means when Boolean statement 1029 becomes true, do I want to delay outputting that true state through this digital output? Or how much of a delay do I want? I say 0. I don't want a delay. Now let's go up here to see what that means. Those numbers we key in there mean exactly. So control outputs, delay on. So it says you can delay activating an output point in increments of 100 millisecond ticks, right? So here, 0 actually means 0. There's no delay. A 1.
Hey, Isaac, we lost you again.
Okay. So let me go back to this. On the delay on, that means any number you key in there is going to represent 100 milliseconds. So if I put a 1 in there, that means I'm delaying outputting that state, a Boolean statement 1029. When it went true, I'm going to delay outputting it by 100 milliseconds. If I put a 10 in here, then that means I'm going to delay outputting it for 1,000 milliseconds, which is 1 second. But I don't want to delay it. So what about a delay off? Well, maybe when Boolean statement 1029 goes off, maybe I want to delay turning the digital off for, let's say, a second or two, right? So if I want it for 1 second, I would say a 10 in there. So even though Boolean statement 1029 goes off, I'm going to wait 1 second before I turn the digital off. And this delay off is helpful for systems that, may not be able to see a digital go on, and then if it goes off too quickly. So the flow computer helps you by saying, if the state changes, I'm going to delay turning it off on the digital output so the other system that's looking at it can see that it came on. But in my case, I want to set it to 0 and 0 now, realizing that 1029 is actually looking at the status of 1911 and 1912, and those don't get reset until a new proof sequence starts. So if a PLC is looking at this, when it sees that it went to 0, that 1029 went to 0 in this digital output, it knows that a proof sequence has now started. And when one of them goes high, it now knows that a proof sequence has ended. Now, if I wanted to be very specific as to which one, let me go back here to the document. So if I wanted to be very specific about which one, I would just assign 1911 to one digital output and 1912 to another digital output that the PLC would be monitoring. And when it sees both of them go to 0, it knows that a proof sequence has started. And then when one of them goes high, it knows that a proof sequence has ended. And that one of them, if 1911 is high, or whatever digital output you assign that to, if that goes high, then you know it was a successful proof sequence. But if 1912 or whatever digital you tie to it goes high, then you know it was an aborted proof sequence. Okay, I think this one was pretty straightforward, but again, if you have any questions on any of these, feel free to give me a call. And let's see what else we got. And I don't know what's different about this one. Okay, we're kind of doing the same thing here. Same thing. Just a different note. Tell you what, let me go back here to Omnicom, and I want to explain some of the operators in here. You know, you see the ampersand and the forward slash, the equal sign, the plus sign, and you see some of those same ones here. So let's just go in there and look at the Boolean statements first. And there's several examples in here of each operator. And by the way, if you know Allen Bradley programming, a lot of these operators really function the same way as in an Allen Bradley PLC. It's just unique operator symbols in the Omni. So it gives you examples in here of the not operator, which is the forward slash. Now, in a variable statement, this symbol represents divide by. It does not represent not, although there is one situation in a variable statement where it does represent not, and that's if it's the very first character in the variable statement. Let me see if I've got any examples here. Like here, for example, right? It does not, if it was in any other position in that statement, that operator would mean divide by, but since it's the very first symbol in there, the Omni knows you're checking to see that 1112 is not true. So in this case, if, which is the close parentheses there, I know it's hard to see, it's kind of small, but if 1112 is not true, and remember 1112, that was the batch in flag acknowledge for meter 1. But it's not checking to see if a batch is ended. In this case, it says if a batch has not ended, right? So if 1112 is not true, then transfer whatever was in this scratch pad register to 5591, right? And it's doing the same for meter 2, meter 3, and meter 4, right? So let's go back to the operators again and the help. So again, the not. And it gives an example here. And remember what we wrote earlier too. Turns off meter 1 totalizing and frequency is below the active frequency setting. So we covered this one. Now the next one is the not. Well, I'm sorry, the end. We just covered that. All variables to the left and right of this operator must correspond to the logic they are being checked for, true or false, before the Boolean statement is considered to be true. So in this case, we're creating a momentary to detect a change in digital input number 2 from a low to a high state, thus making statement 1025 true during 100 millisecond update cycle. Now, one thing I have to say about the Boolean statements is the Omni processes them every 100 milliseconds. So basically, the Omni does the updates of the registers every 500 milliseconds, every half second. So in that 500 millisecond cycle, it actually scans those statements and processes them 5 times. And the value that you will see in there at the end of the 500 millisecond cycle is the last time it read and processed those. And the variable statements are only processed once every 500 millisecond cycle. So it does create some timing issues for you sometimes. So it's very important that you test the statements when you write them so that you know that they work and that you haven't run into any timing issues. But there are some registers in the Omni that are momentary registers, like 2 seconds, for example. So you can stretch them out when they come on so that the variable statement, if it is calling a Boolean statement, can see them. Remember we talked about the delay off on a digital output? Well, you've got operators in here that will do the same thing. When the state changes from a 1 to a 0, you can delay it from turning off by capturing it in a 2-second momentary. So here in this example, it says 1002. Well, what is 1002? Let's find out. It says digital IO point number 2. So whatever state that digital channel is in, it captures it. So 1002 XOR, right? Even though it's using an AND here. The example is for this operator, but they're also using this operator, the XOR. 1026. What's in 1026? 1002. Same thing as we saw up here, right? But this is from the previous scan cycle. So it's checking to see if it changed, if it toggled. And then it qualifies it here by saying it has to be true. So we're checking for a 0 to 1 change in state. The XOR or compare the current state of digital input number 2 with the previous state of digital number 2 saved in the previous 100 millisecond cycle to see if there's been a change of state, and check to see if the change was from a low to a high state. All right, so that's the, in that case, if that all of that is true, then Boolean statement 1025 will be true. But if there was a change, but 1002 is not true, in other words, it didn't go from 0 to 1, maybe it just went from a 1 to a 0, then 1025 will not be true. All right, so that's the AND operator. We go to the OR. Either the variable or logic to the left or to the right of this operator must correspond to the logic being checked for true or false before the Boolean statement is considered to be true. So here we're checking 1105 or 1205. Now, remember, this had to do with the active frequency. So 1105 is for meter 1. Once it goes above that active frequency threshold, for the pulses coming in, then that meter will be considered active. 1105 will go true. So here it's checking to see if either meter 1 or meter 2 are active. And that's about it for the OR. Pretty simple one. Now the XOR, again, we talked about this. It's, and actually it points you back to that AND one where we saw it over there. The XOR just means the opposite of. And the equal, that's pretty simple. However, it's important to know that that equal here means that you're transferring whatever's on the right to the left of that equal sign. It's not the other way around. You're not transferring 1719 to 1026. You're transferring 1026 to 1719 is what you're actually doing. 1719, again, let's look to see what that is. And that's the request a snapshot report. So they're saying a Boolean statement 1026 is true, or actually it doesn't care if it's true. It's just saying whatever value it is, transfer it to 1719. So if it's false, it's going to be sending a 0 to 1719 constantly. And that means it's not going to request a snapshot report. But if 1026 ever does come true, then it's going to send a 1 to 1719 and a snapshot report will print out. Now, this statement is not written correctly. Remember what I said earlier about command points should be equal to themselves? So it should read 1719 equals 1719 or 1026. Because the way this statement is written, 1719, you could write to it via the Modbus, But remember that the keypad also writes to that. So if you're not entering a request snapshot command from the keypad, it's constantly sending a 0 to that command point. So if you write to 1719 via Modbus and the keypad is writing a 0 to it, you have a conflict. So you may get your snapshot report if you were able to sneak it in there, sneak the command into the Modbus register, or you may not, depending on exactly when you wrote the command or wrote to the command. So it should read 1719 equals 1719 or 1026. That's actually how it should be written. So we have the go-to. Use the G operator, which is the go-to, to change the order of statement execution by going to the Boolean statement number following the G. So it's basically like a jump. You're jumping over statements. It must be a valid statement number between 1025 and 1088. So in this case, example 1, go, it's using Boolean statement 1031 and it says go to 1040. So it's basically going to skip 1032 through 1039 is what it's going to do. And sometimes this is a good statement to use for troubleshooting when you want to see if one of the statements that you've written is causing you a problem, then try to skip it by jumping over it with the go-to statement and see how the flow computer behaves. And here, if 1719 is true, jump to statement 1040. So we already discussed earlier that 1719 is the command to request a snapshot report. So it says if a snapshot report has been requested, and again, the close parentheses means if. So if 1719 is true, because it doesn't have the slash in it, otherwise with the slash in front of it, it would mean if 1719 is not true, right? But in this case, it says if 1719 is true, in other words, if a snapshot report has been requested, then go to statement 1040. So skip 1032 through 1039. But here we see it's checking to see if it's not true. If the snapshot report has not been requested, then jump to statement 1040. So the if operator. So the if is basically just that close parentheses. So it says if 1105 is not true, or I'm sorry, if 1105 is true, right? Because it doesn't have the not in front of it. So it says if 1105 is true, in other words, if the meter 1 is active, then go to statement 1042. And there should not be a space here as this example shows. No spaces are allowed in the statements. That goes for the Boolean or variable statements. The move range operator. So this basically saves you a lot of statements. What this statement is doing here, and the if operator is the colon symbol. So 1501, if we look that up, that is a scratchpad Boolean register, right? So, and 1105, we already said is the meter 1 active flag, but it wants to move this entire range, 1105, 1106, 1107, 1108, 1109, and 1110. So it wants to move those 6 registers over to 1501 through 1506, right? So instead of having to write 6 individual Boolean statements to transfer 1105 to 1501, 1106 to 1502, 1107 to 1503, and so forth, you can do it with just one statement. And this is your range that you want to move, and the flow computer knows how many registers are on the right and the starting register on the left. So copy points 1105 through 1110 into scratch patch points 1501 through 1506. So it's very handy. And you can do that with any type of register. In this case, they're Booleans, but you can do it with 16-bit integers, 32-bit integers, floats, strings, ASCII strings. So timer function. This is where I was talking about stretching some of these so that they can be seen by the flow computer or some other system reading them. So if you will, this is like the delay on, that 50 in there, and the 100 is like the delay off. If you can imagine assigning 1501 to a digital output. So you would assign 1501 to a digital output. For the delay on, you'd put 50, and for the delay off, you'd put 100. But if you don't want any delays at all, you would put a 0 in here and a 0 in here. Now, in this case, they may not be assigning this to a digital output, but maybe something like a PLC is reading this register and it needs to be left on long enough for the PLC to read it. So in this case, they could come in with the PLC and they could read 1640 or they could read 1025. Either one would give them that state. And what is 1640? Let's go look. So again, that's a scratch pad Boolean, but it doesn't actually give a good description in here because it is a 2-second momentary is what it is. So you have, well, I take that back. This is 1650 is the 2-second momentary is where they start. So that's not a good example here. That should say 1650 here. Right. 1650 equals 1501. 1501, remember, is the first Boolean scratch pad. And 50, 10, well, we already talked that was the delay on and delay off, right? Okay. So where 1640 is the target timer, 1501 is the trigger Boolean. So we're really looking at the state of this register. And then if it goes off, we want to leave it on for 100 times 100. So that's 10 seconds. That's 10 seconds after 1501 goes off. We still want 1640 to be on or 1025 to be on. A rising edge. Sometimes we just want to see when a status point goes from a 0 to a 1. And that's it. We don't want to monitor the on state of it or it going from an on to an off state. We just want to see it at the moment that it goes from a 0 to a 1. So that's what this is. Remember, we had the close parentheses operator, which was a closing parentheses. In this case, this is an open parentheses. And 7599, we already know, is a float scratch pad. 7501 through 7599 are float scratch pads. So it's written in Boolean statement 1071. So statement 1071 will be true for 500 milliseconds when the value in Modbus register 7599 goes from a negative value to a positive value. Note that 0 value in 7599 is considered positive. So that's a very important point here, right? So Boolean statements here is calling a float. So, and if it were to call an integer, whether it's a 32-bit integer or 16-bit integer, a value of 0 in an integer means it's on or positive or true. The same way that a value of 10 in any one of those register types would be on or true. So if you look for a 0 value in an integer is always going to be true. So it's not a good idea to look for a 0 value or a true value in an integer because it's always going to be true. Now, a floating point register can be a negative number or a positive number. So in this case, they're looking for a value of negative to positive, maybe a -1 to a 0, or a -1 to a 10, or a -1 to a 20, or any negative number to any positive number. That transition, that's what they're looking for. So it's very important that when you write a Boolean statement, you realize that, because sometimes let's say this was, instead of scratchpad 7599, maybe it was calling variable statement 7025. And depending on what you have in 7025, 7025 may always be true, right? 7025 is also a floating point register, by the way. So you can actually have a value in that variable statement that can be a negative or a positive. But in this case, it's looking for scratchpad 7599 to go from a negative to a positive value. So 0 is positive, something very important to keep in mind. And so that's going to be true at that moment for 5 milliseconds, and only for that long. Now, if you wanted to stretch that for more than 500 milliseconds, then you could use the timer function operator and stretch it. Okay, here's the falling edge. Same concept, but the other way. So again, the open parentheses, and then we insert in front of it the not operator. So in this case, we're looking for the transition from on to off. And then we have the one shot. That's the @ symbol. This operator is used to detect a changing state, either from a positive to negative or a negative to positive. Just a toggle. That's all we're looking for. So up here we had the rising edge, and then we had the falling edge operators. This one covers both of them. Just a toggle. And then we have the user-defined alarm messages. So you can create custom alarms in here. And it says statements, Boolean statements 1073 to 1088, that's 16 alarms, can be used to implement user alarms. For applications 23, statements 1057 through 1088 can be used. That's 32 alarms. Application 23 is for US units gas measurement. So here, what they're doing is Boolean statement 1030, although it doesn't say 1030 here. It's actually Boolean statement 1030. They wrote this 1088. So in this one, they're referring to statement 1088. It says equals whatever status is coming in on digital input number 2. And in 1088, instead of writing numbers in it, they wrote this text, high filter DP. Right, so they tied it, that filter to digital input number 2, And when it goes high, it causes that to be transferred from digital number 2 over to statement 1088. When the Omni sees this text, it has no idea what to do with text. So it creates an alarm for it. And whatever alarm message you type in that statement, that's what it creates the alarm as. So high filter DP is what you typed into the statement, and maybe in the remark area. Let's go look at that. So here, they would have typed in and you can type in the same thing here. This is just for your information, right? Or you can just say whatever you want in the remarks. But this is what the alarm will say in the alarm log when you, or when that digital number 2 goes high. So basically what they did here is in statement 1030, which is way up here, which is in use already, but we could have used any statement. So 1088 equals 1002. High EP alarm. And then that 1088 high filter DP is what will appear in the alarm log. And it says here, note, do not use a statement or Modbus register number in the custom alarm statement. And they're saying this is invalid because it doesn't know how to handle a mix of high filter DP and the number. Okay, this one, using integer and floating point variables in Boolean statements. So point numbers for normal integer and floating point number variables can also be included in Boolean statements. Positive values will be registered as true, negative values as false. So the example it gives us here is in statement 1031. It says 1719 equals not 7801. So let's see what they're doing here. 7801. Station gross flow rate. Now a station flow rate can be either positive or negative. A meter run flow rate will always be positive, but a station may be negative because you may define the station as 1 minus 2 plus 3 minus 4, something like that. So your station totals can be negative, and therefore your flow rate could be negative as well. So it says if station flow rate 7801 reverses, it goes negative, trigger a snapshot report. So it says that's the command point, right? And again, I don't like the way this is written. It should say 1719 equals 1719 or not 7801, because we talked about keeping the command point the same. 1719 equals 1719. So at that moment, you're going to get a snapshot report. Actually, I don't know if it had another example here. That's the only example. Boolean statements can include integer register moves to Boolean variables, and Boolean variable moves to integer registers. So what this is doing is it's unpacking, or actually packs, I'm sorry. This is a packs example, whereas the one down here is an unpacking example. So these are Boolean bits. 1501 through 1599 are actually Boolean scratchpad registers, right? But it's taking the first 30 and it's transferring them to 3501. Now, 3501 is a 16-bit scratchpad, so you can't fit all 30 bits into that 16-bit register. So the Omni knows that. So what it does is it uses 3501 and 3502 to contain those 30 bits. So 1501 through 1516 go into 3501, and 1517 to 1530 will automatically go into 3502. And then it packs zeros at the end of the other bits in 3502. And this one is an unpack. If you've got two registers, 3501 and 3502, if you've got that range of registers and you want to unpack them, then it knows that it needs 32 bits. So 1501 through 1532, it'll unpack those bits and put them in those 32-bit scratch pads, Boolean scratch pads. Okay, so the current state of any input or output point can also be used in programmable Boolean statements. So IO points 01, in other words, digital channels 01 through 12 are automatically in the flow computer assigned 1001 through 1012. And for the second module, it's 1013 through 1024. So that's just a note to tell you how the Omni treats those internally. And then the scratchpad Booleans. Boolean points 1501 through 1649 with the exception of 1600, which is reserved. So this is very important here. If you try and read from the Omni 1501 through 1649, you're going to have a problem. You need to read 1501 through 1599 and then pick up with another poll at 1601 through 1649. Okay, and that's all the Boolean operators. And we're almost out of time here, but you can actually go and look at the variable statement operators in here as well on your own time, and it'll give you examples in here of the operators that are accepted in the variable statements. And here's examples: the equal sign, the go to, the if, the move range. Now, the exact compare is something that you only use in a variable statement and not in a Boolean statement. Same thing with the indirect reference and the right ASCII string, the totalize. Those are unique over here, but all the other ones, you can also use them in the Boolean statements. And you've got all these other ones as well, the absolute, raised to the power of, the multiply and divide. This was an XOR symbol over there in the Booleans. Over here, it's a multiply. It was a not in the Boolean statement. Over here, it's a divide. And then it was an or in the Boolean statement. Here, it means plus. And then you've got to subtract here as well. And it gives you examples on how to do each one of those. There's several examples in there. So the statements are powerful. And in many of the older versions, you had 1025 through 1088, and that was it. But in the later versions, they added even more. They added another 64. So now you got 128 Boolean statements. And the same applies to the variable statement, D25 through 7088. But in the newer firmware, they added another 64. So you can do a lot. Here, I'm just capturing the batch pulses into scratch pads because the Omni actually gives you pulses for the batch in progress, but it doesn't transfer them to a previous batch registers at the end of the batch. So you end up losing those in the older versions of the phone. Anyway, that's about it. I want to thank everybody for attending today's session. And I really apologize for the problems I was having earlier with the audio. Hope to get that resolved for next time so we don't have to deal with it. There will be other classes like this. We'll talk about other things. Maybe even cover the Omni 7000 and its differences. But anyway, thank you very much. Again, if you have any questions or need these examples that I gave you, if you need them, I'll be glad to provide them to you. So again, thank you very much. Have a great day. And I appreciate you attending. Thank you so much. Bye.
Thanks, Isaac.
Mm-hmm.